Hi everyone, how are you? Can everyone hear me? I hope so. We're all getting started. Well, welcome to our live solve. I'm Po-Shen Loh. I am actually at home. Usually I join these things from all different parts of the world. Oh, hang on. Samarth is not far from my home. That's my guess. Yes, because that dorm room looks familiar. But anyway, well, they'll introduce themselves in a short while. But let me first say welcome to everyone. It's a great pleasure to work together with Math League. They have a good set of questions every month, and sadly, we don't have time to do all of them. But it's always great when people come up with these questions that will give us a little bit of challenge. I don't know if any of you guys do math counts. Math counts competitions are going on right now. Please do not discuss the questions at all in our chat because people are doing math counts in many different cities, okay? But nevertheless, this kind of a contest gives you a chance to practice for it, okay? And so we are very happy that every second Sunday we always work together with math counts. Now, during this live solve, you might notice that you guys get to type and talk. That's more fun. So if you haven't used this thing before, just send messages directly to chat relay and they'll appear at the bottom of the screen. During the actual live solve, I recommend you use speaker view because I'm guessing that it'll be easier to watch the incredible instructors teaching if it looks big. So right now we did spotlighting for everyone, but when the spotlights disappear, if it goes into this gallery mode where everyone's really small, just go to the corner of your Zoom, press to the speaker view, and then you'll be able to see everything nice and big. Okay, and now what we always do, these are live solves, and what that means is you'll get to see how professionals actually think through things if it's the first time that they ever saw them. This time we have some incredible guest hosts. Well, they're actually instructors in the live program. If you have seen what we do, we teach math online with this program called Live, and everyone looks far more interesting than I do. And with that, I'll pop it over to Arit and Samarth, and they're going to take everything from here. So, Arit, why don't you start with the intros?
Of course. Thank you for that. Okay, thank you for that introduction, Dr. Po-Shen Loh. I'm Arit.
And I'm Samarth, sorry.
All right. So, and Samarth right now, and Samarth is actually a really cool person. So, first of all, currently he's a freshman at Carnegie Mellon, which is actually Professor Loh's alma mater. Before that though, he was a three-time Amy qualifier. Which, if you don't know, the Amy or American Invitational Mathematical Exam is a really prestigious math competition, and he's also a let's see. He qualified for Math League Nationals since fifth grade. He's he's a officer at his school's chemistry Olympiad team, and he actively participated in his school's math team. Besides that, though, he enjoys tutoring people, such as you guys, reading books, public speaking, and playing table tennis. Respect.
All right, thank you, Art. Art's been glazing me a little bit, but honestly, I don't think I can hold a candle to this guy. He's also a three-time Amy qualifier, despite being quite a bit younger than me. He's also placed in multiple other competitions, including FAMAT, and also is ranked in the top 15 at Florida State Math Counts. In addition to that, he appears to be an amazing engineer. He's built a smart irrigation system, he engineers his own custom drones, and he contributes to a world's qualifying FRC robotics team. He has multiple medals in astronomy at Science Olympiad, and his hobbies include playing electric guitar, frolicking, and attempting to fold origami. So, of course, it is a huge honor for me to get to teach with Art today.
I can say, and I'll say the same to you, Samarth. So okay. So first of all, thank you guys for being here. I know a lot of you guys are about to be watching the Super Bowl. In fact, let's pose with a pretty quick question. Type in the chat, who do you think is going to win the Super Bowl series this year? Personally, I think the Seahawks have a pretty decent shot. What about you, Samarth?
I don't follow football that closely, but a lot of my friends are like diehard Seahawks Glazers, so I'm gonna have to go with Seahawks as well.
All right. And it seems like the chat is in. It seems like the chat agrees with us mostly.
Huh.
There's a few Patriots. There's a few Patriot fans though. All right.
Okay, now it's shifting. Oh, now momentum is shifting.
Mm. All right then. Uh, okay. Now that we got out of the way, let's try and get started.
All right.
Okay. So let's start with this first question. In a classroom, each student has either one pencil or two pencils. Given that there are 20 students who have 26 pencils in total, how many students have exactly one pencil? To me, this seems like a pretty classic systems of equations problem. What about you, Samarth?
I agree. And considering it's a systems of equations problem, I think our first step should probably be to actually figure out what our equations are going to be. So to start, let's declare two variables. I'll have my first variable a be the number of students with one pencil. And then, do you guys have any guesses for what our second variable should be?
Let's see. I think I'm seeing that a lot of the people are saying that the second variable should be. Hmm. Oh, I see a lot of answers in the chat.
Oh, wow.
Uh, Hmm. Let's see. But personally, I think the second variable should simply be the amount of students with two pencils.
I agree.
So, yeah. So if we okay. So once we get those two equations, I think we just have to set them one equal to and we have to set one equal to the other. So, students with one pencil and student with two. Oh, all right. Sorry for that delay. So,
All right, so yeah, as Art was saying, basically once we have our two variables, all we have to do is set up our two systems of equations. Our first system is going to be the number of students, which because we are given in the question that's equal to 20, we can say a plus b is equal to 20. And then our second equation is going to be the total number of pencils that each student holds. We know that every student accounted for in A has one pencil, and every student in B has two pencils. So when that means that our equation should equal a plus 2b is equal to 26, because every student in our category A is going to contribute one pencil, and every student in B will contribute two. So when we have these two systems of equations, what we can do is we can subtract the top equation from the bottom equation to get B is equal to 6, where 6 is the number of students with two pencils. And since the total number of students is 20, the number of students with one pencil is going to be 20 minus 6, which is equal to 14.
that sounds pretty good. So we've stopped. Okay, so that seems like a pretty cool answer. But before we move on, we have to first plug it in back to this problem. So what we've gotten is that a is equal to 14, and that b is equal to 6. But is that really true? Wait, a is equal to 14, b is equal to 6. Let's see. If there are 14 students with one pencil, that's just going to be 14 plus 2b, and that has to be equal to 26, as we discussed before. And we found that b is equal to 6. So what's 2 times 6? Let's type in the chat. 12. Pretty good. So we got 14 plus 12, which is simply 26. So we're right. And let's see if that question is correct. Yep, we got it.
All right.
All right, that was pretty nice.
Okay, this seems like a fun one. Our next question is, what is the greatest integer n that is a solution to the inequality n plus 2 over 2n plus 1 is greater than 7 over 12? Alright, what do
Hmm.
you think our first step should be while solving this problem?
Let's see. I don't really like this. I don't really like this greater than sign. So, and also I don't really like these fractions. These look pretty ugly. What if we try and cross multiply them? I think that's a pretty good way to start it out.
I like that. So, our first step is going to be simply cross multiplying our inequality here. Oh, let me get there. Anyways, so with that in mind, this inequality is going to be equivalent to saying 12 times n plus 2 is greater than 2n plus 1 all times 7. Keep in mind this is because what we're doing is multiplying both sides of the equation by the denominators to get rid of it. Now that we have this, what we can do is we can actually expand out both sides of this equation to get 12n plus 24 on the left and 14n plus 7 on the right. And
Hmm.
all right, from here, what would our next step be?
Let's see. So right now we have that 12n plus 24 is greater than 14n plus 7. But that doesn't really tell us a lot. What if we do what if we subtract what if we assume there's an equal sign? That way we can subtract it and then we could try and find n.
Okay, I like that idea. So for now, we're going to move away from our initial problem, and we're going to instead try solving 12n plus 24 is equal to 14n plus 7. And from here, we have a fairly simple system. We have a fairly simple linear equation to solve. So we can move all n's to one side. So we get 2n on the right by subtracting 12n from both sides. And we can get 17 on the left by subtracting 7 from both sides. So we get 2n is equal to 17, or n is equal to 17 over 2, which is equal to 8 and 1/2.
Yeah, that seems like it would work. But that only tells us what n is equal to. We have to try and find this. We have to try and find the greatest. We have to try and find the greatest integer n that is the solution to this. And it doesn't seem. And it doesn't seem like 8.5. And 8.5 is the one where it's equal to. It's not greater than. But I don't. But I think that might work in our favor, because here's the thing: we know that with 8 1/2 we achieve equality. That this side is equivalent to this side. But what if it's a little bit less than 8 1/2? Let's say 8. Let's try and plug this in. If we substitute 8 for n, we get that 10 over 21 is greater than 7 over 12, which it seems like, and by cross,
Sorry, I think you meant to say 10 over 17.
10 over 7, 10 over 17, right?
Because we're
No,
plugging in 8, right?
8,
Oh
yeah,
my,
so 10 over 17. My apologies.
what happened
So if we once we do cross multiplying, we get that 120 is greater than 119, which seems like it should be right. What do you think?
I agree. But now we have to double check that this is also the greatest integer. So maybe we should try plugging in a larger number.
Right. And what's the integer after 8? Well, that'd be equal to 9. So, if we plug into 9 to this, we're supposed to get that 11 over 2 times 9 plus 1, 19, is greater than 7 over 12. But after cross multiplying, it doesn't seem like it's the case, because 11 times 12 is what? 132, and 19 times 7 is equal 19 times 7 is equal to 133. Ooh, that doesn't seem like it works out. What do you think, Samarth?
That seems like a contradiction. So we know that 8 works. We can assume that numbers less than 8 work as well. And we know that 9 doesn't work, so numbers larger than 9 also shouldn't work. So when we put these two facts together, I think it's fair to say that the largest integer that satisfies this problem is in fact 8. Are we ready to check?
Yeah, let's try and do it.
All right,
Oh, am I right?
good stuff. One quick note about this problem. We did end up trying to go about this problem by first solving for equality and then testing values lower than or higher than. But actually, some of you might have noticed that you can actually take the process we used to solve for, like equality for n, and we can actually do the same process with our inequality over here. So, just the way we did, we could have instead simply done all of these operations on the inequality itself. So subtracting 12n from both sides, we could have got 24 is greater than 2n plus 7. And then subtracting 7 from both sides, we could have gotten 17 is greater than 2n, which is the same as saying that 2n is less than 17, or n is less than 8 and 1/2. So
I
a
agree.
quick note for inequalities is you can always just do whatever operations you would do with any equation on an inequality. Just make sure that you're careful to preserve the sign. Remember that addition and subtraction don't actually change the sign, but flipping the equation does reverse the sign, and multiplying by a negative number also reverses the sign.
I think that's really important to note, Samarth, because using this method, it looks like it's really powerful. We use it to solve a seemingly complicated thing, but it's also more to keep in mind its limitations and how to overcome those. That's a really good note, Samarth. Yeah. Well, on that note, let's try and look at the next problem. The arithmetic mean of 5 integers is 20. Given that the arithmetic mean of 2 of the numbers is 26, what is the arithmetic mean of the other 3 numbers? First, let's try to find what arithmetic mean is. In this case, if you have k numbers, the arithmetic mean is just a1 plus a2 all the way plus ak all over k. So basically it's the average. Now in this case, we're given the arithmetic mean of 5 integers is 20. So a1 plus a2 plus a3 A4, and A5, all divided by 5, is going to be equal to 20. Now, this seems like pretty complicated, but Samarth, the next part of this problem, how do you think we can integrate this?
Yeah. So, I think one thing that's really useful to note is that we can actually take this and we can convert it to be directly a sum of the numbers. We know that if the average of all these numbers is 20, then the numbers themselves have to actually add up to 100 because we can multiply both sides of this equation by 5 again, right? Multiplying this side by 5 and this side by 5, you get that these two numbers multiplied to 100. Okay? So now let's pretend that the numbers that are relevant, in this case, the two numbers that whose arithmetic mean is 26, let's just pretend that those two are a1 and a2. If the average of two numbers is 26, then what must their sum actually be? Alright, do you want to help us out here?
Sure. So let's take a look at this. It's given that the arithmetic mean of two of these numbers is 26. That's just given that a1 plus a2 all over 2 is equal to 26. But you introduced a trick before. If we simply cross multiply both sides by 2, we get that a1 plus a2 is just equal to 26 times 2, which is equal to 52. So I think those two numbers just sum to 52.
I agree. So in that case, what we can do is we can actually take these two values in our equation and we can plug them in for 52. So now we know that a3 plus a4 plus a5 plus 52 must be equal to 100. Here, let me make some more space so it's more obvious.
Yeah.
All right, so this is our new system of equations. Keep in mind our goal is to find the arithmetic mean of the other three numbers. So now, since we have this equation, what we can do is we can subtract 52 from both sides to get that a3 plus a4 plus a5 is equal to 48. But this
This
is the equation we want. What we want is the mean of these three numbers. So how can we modify this equation specifically to get the mean of these three numbers? Everyone, you can put your answers in the chat, and then
Let's see. A lot of them are saying to divide it by 3. And honestly, I'd have to agree with them because our definition for arithmetic mean is just a1 plus a2 all the way to ak divided by k. In this case, k is equal to 3. There are 3 different numbers. So the process before where you multiplied the number to get the total sum, I think you do the reverse, where you divide this number by 3 to get the arithmetic mean. And what's 48 divided by 3? Well, that's simply equal to 16.
and now checking our answer,
Hopefully.
see that we are correct.
Let's go.
Wonderful.
All right.
Ooh, this is a fun one. I always love combinatorics questions. Okay,
Perfect.
all right, do you want to get us started?
Sure. In how many ways can the digits of 1, 2, 3, 4 be arranged to form a four-digit whole number greater than 1, 2, 3, 4? This is a pretty interesting problem. 1, 2, 3, 4 is a classic number, but more importantly, it's actually, in some ways, I think this might be the smallest possible number where you can arrange the numbers 1, 2, 3, 4. Because what makes a number large? Well, Samarth?
Yeah. All right. So let's think about this, right? Let's say we have the numbers 1, 2, 3, and 4, and we want to arrange them to form a number. If you were to form the biggest number possible, the largest digit you have access to is the number 4. Where would you want to put it? Obviously, you would want to put it in the thousands digit because that is the digit that contributes the most to the actual value of the number. Any smaller number going in the thousands digit just puts a hard cap on the value of your number, right? So conversely, if you were going to construct the smallest possible value for your number, you would want the thousands digit to be the smallest possible number. In this case, 1. Keep in mind we're constructing the smallest possible number right now.
All right. And
You're
same
gonna have
and same with and following your logic, if you want to create the smallest possible number, I think the second largest digit, which is the hundredth digit, must have the second smallest number. Now, what's the smallest number after 1? Well, that's just 2. And as people are putting in the chat, if you keep on following this pattern, you get the smallest possible number to be 1, 2, 3, 4. And if you follow the reverse logic or the converse, you get that the largest possible number is equal to 4, 3, 2, 1. But this problem is asking us how many ways can digits of 1, 2, 3, 4 be arranged to form a 4-digit whole number greater than 1, 2, 3, 4? Well, we've established that 1, 2, 3, 4 is the smallest possible number, but how many different ways are there to arrange the entire thing?
Great question.
Let's see.
We can think about constructing a 4-digit number as, like we've been doing here, basically placing each of the digits of the number into its own little bucket. So, when we are constructing an arbitrary 4-digit number with these 4 digits, our first digit, we're always going to have 4 choices for it. So the number of ways to assign a first digit is going to be equal to 4. By a similar logic, our second digit can be any number out of the 4 except the first one that we already chose. So our number of options for this number is 3. And then again, for our third digit, we can have either of the 2 remaining numbers. So we have 2, and then our last digit is fixed from there. So the total number of rearrangements of the digits 4, 3, 2, 1 is going to be equal to 4 times 3 times 2 times 1, which is equal to 24. So is our answer 24?
Doesn't seem like that, Samarth, because even though there are 24 possible combinations, we still have to eliminate the ones that don't work. In other words, ones that aren't greater than 1, 2, 3, 4. Luckily, though, this won't be too hard. We've already established that 1, 2, 3, 4 is the smallest possible number. Anything else is greater than that. So the final answer is just going to be 24. It's just going to be 24 minus 1 for a total answer of 23.
All right.
And I see people in the chat agree with us. Let's
That's a
see if
good
it's
sign.
let's see if we're correct. All right.
Looks like we are.
Let's go. Ooh, this is a long one. Samarth, you want to try and do this in one breath?
All right. Jane has 3 different shirts, 3 different pairs of shorts, and 4 different pairs of socks. Every day, Jane wears an outfit consisting of 1 shirt, 1 pair of shorts, and 1 pair of socks. However, she does not want to wear any of her green pairs of socks or her pink pair of shorts today. How many outfits can Jane wear today?
That's impressive. Oh,
Okay.
wow. All right. For those of you who might not understand, let's maybe say it. Jane has 3 different shirts, 3 different pairs of shorts, and 4 different pairs of socks. How every day Jane wears an outfit consisting of 1 shirt, 1 pair of socks, shorts, and 1 pair of socks. However, she does not want to wear her green pair of socks or her pink pair of shorts today. How many outfits can Jane wear today? First, I'm trying to figure out how many different combinations are there. Well, this seems a bit similar to our previous. This actually seems pretty similar to our previous problem, doesn't it?
Yeah, I agree. So we can actually think about this problem as picking one article of clothing from each of our 4 different buckets. But keep in mind we have some extra information that we have to consider here. Jane does not want to wear her green pair of socks or her pink pair of shorts today. So originally, when we're constructing an outfit, we would simply pick a shirt from this bucket, pick a pair of shorts from this bucket, and then pick a pair of socks from this bucket. However, we have to keep in mind that one of our pairs of socks and one of our pairs of shorts is off limits. So we can effectively cross those out. So now our problem has simplified from doing all of that to simply picking 1 shirt from our allowed list of shirts, 1 pair of shorts from our allowed list of shorts, and then 1 pair of socks from our allowed list of socks. And Arth, how do you think we'd go about computing the number of ways to do this?
I think that's a Let's see. We have 3 ways to choose a pair. We have 3 ways to choose a shirt, 2 ways to pick a pair of shorts, and 3 ways to pick a pair of socks. So this may seem a bit naive, but I think the answer is just 3 times 2 times 3, which should come to a total of 18.
I agree.
What do you think?
I agree. So let's just see if we're right.
All right.
And it looks like we are. This is a fairly standard practice we do in competition math, where basically it's called constructive counting, where when we're trying to figure out the number of ways we can do something like construct a number or pick an outfit, what we do is we think about how many choices we have at each step of the selection process. So for the last problem, it was picking a number for each digit, and in this problem, it's picking a different article of clothing for each different article of clothing that goes into an outfit. And then if the number of choices is the same at every step in the process, then you can simply multiply the number of choices you have at each step to get your final answer.
Don't you guys just love it when tricks like these come with competitions? All right.
On to our next
Ooh,
problem.
we're taking a break from counting with this one. In the expression 1, circle 2, circle 3, circle 4, each circle is replaced by a plus or a multiplication sign, and the final expression is then evaluated according to the order of operations. How many such expressions evaluate to 10?
Now,
Okay.
when I first look at this problem, to me it seems really complicated because I have, what, two options at each of our dots? That's eight total options. But I noticed something really interesting off the bat that helps me simplify this a lot. Look at look at the dot between 3 and 4. And imagine if this dot was a multiplication symbol. Then, because both plus and minus are basically multiplications, we would have 1 dot 2 dot and then 3 times 4. But we know because of our order of operations that this number would because of order of operations, this would be evaluated first. So that means that our total sum would be at least 12 off the basis of this number alone. That's a problem because we need our expression to sum to 10. And that means that if we put a multiplication sign here, it's impossible for the rest of our sequence to sum to 10 because we can't go down. So off the rip, what that tells me is that at the very least, the symbol between 3 and 4 must be a plus sign.
And honestly, I think I could see the same logic applying to 2 and 3 as well. Let's take this. Let's suppose there's a multiplication symbol between 2 and 3. You put 2 times 3, that's equal to 6, and then it's 1, it becomes 1.6.4. Ooh, but I see a problem. Both of these have to be either plus signs or times signs. But oh wait, I see a pathway. What if we do 1 times 6, but then this dot would be equal to 4. This dot would be equal to plus, and that would be equal to 10. Okay, seems like we found a way.
But now we know that what we need is we know that we need these first three numbers and the dots in between them to get to 6. So we know that 1 times 2 times 3 is equal to 6. But is there another way to get 1, 2, and 3 to combine to equal 6 somehow? I think there is.
Yeah.
Because if we add 1, 2, and 3, then we end up getting that 1 plus 2 plus 3 is equal to 6. And then if we were to add in our last little dot, we get that 1 plus 2 plus 3 plus 4 is equal to 10.
And yeah, this seems like it'll work, and it does. But do you think there's another solution, or is it just 2? Because 2 solutions seems a bit low.
I claim that actually this is the maximum number of solutions we can have. We already established earlier that this dot here cannot be a multiplication symbol. We know it has to be a plus. So that already locks us out of 4 options for these possible dots. And then, when we plugged in arbitrary values of multiplication or addition for the dot between the 2 and the 3, we ended up figuring out that the dot between the 1 and the 2 had to be one specific operation to get to a solution. Which means we know that we've checked all other possible cases of operations. Any other possible permutation of what symbols go in what dots is accounted for in one of the cases that we have already established is not going to get us to 10.
That sounds perfect. Yeah, and honestly, I agree with you. I think there should only be 2 solutions. Let's see if MathLuke says the same. Are you ready to check? All right.
Yep. And it looks like we are correct.
Correct. Cool.
Let's go. All right. So, for our next problem.
See.
At the Leaguean Mathematical Olympiad, each of the 3 problems can be scored as 0, 1, 4, or 5 out of 5. A competitor earns a gold medal if the product of their scores on the 3 problems is at least 20. How many possible sums of problem scores can a gold medalist attain?
Ooh, another combinatorics problem. Let's see. Right off the bat, I see that there's at least one number here that we have to exclude. So I think the number has to be, and Samarth, you know what the number is? It's 0.
Agree. Because if 0 were to be the score for any of our questions, then we know that the product of our scores would be 0 times some other number, which we know has to be equal to 0, which means that none of our scores can be 0, and we're going to have to get our scores some other way.
And also, let's take a look at this case known as where one of the numbers is 1. 1 seems like a pretty bad score to start off with. for one reason. A, who wants to get a 1 out of 5 on something? And B, let's take a look at our other combinations. The product of the scores on the three problems has to be at least 20. But look at our other options. We can either put a 1, 4, or 5 for 1, 4, or 5 for the others. So if we put a 1 here, let's say, then a max thing we can put here is a 5. 1 times 1 times 5, that comes far below our expectations. That comes far below 20. However, there's some hope. Let's put our second option, 4 here. If we put a 4 there, then it becomes 5. Then if we multiply that by 5, it would be equal to 20. 1 times 4 times 5 is equal to 20. That works. But also, let's assume we can put a 5 here as well. We have 5 in the middle as well. 1 times 5 times 5, that's equal to 25. Again, that's gold medal territory right there. So, if you have a 1 here, then there's 2 possible solutions. But it's a bit more. But there's got to be more. What if we don't use a 1, Samarth?
Yeah. Okay, so right now we've exhausted all the cases where we have a 1 as one of our scores. So we can put those aside for now. That means we're only selecting from 4 and 5. Now, if we can check and see that if we have 3 numbers and all 3 of those numbers are either a 4 or a 5, then our total product is guaranteed to be well above 20. Right? So now our question is, how many 4s and how many 5s are we actually going to put into how many 4s and how many 5s are we going to have as scores? And then our options basically go like this. We can draw a little chart. We know that we have a total of 3 scores, so we can have, let's say, 3 4s and no 5s. Or we could have 2 4s and 1 5. Or 1 4 and 2 5s. Or 0 4s and 3 5s. Now, these are the possible scores we can actually get. Now we have to figure out how we're going to take this and translate it into specific sums of problem scores.
That seems like it would take a bit of time, but actually no. I think there's a fast way to do it. Let's start right off the bat. If there's 3 4s, it just becomes 4 4 4 4 4, and that's just 4 plus 4 plus 4, which is equal to 12. Then let's start with this. Then we get 4 4 4 4 5, and the end that'd be equal to 4 plus 4 plus 5. That'd be equal to 13. But also, I don't think we have to even continue with this. We don't have to continue with this because there's just 4 other possible scores: 12, 13, 14, and 15. Because 4 and 5 are relatively prime, which is another thing. But there are four possible cases, 4 possible sums where we're just using 4 and 5s. Pretty interesting. And how many sums did we get beforehand when we were using a 1? Well, let's look back. We got 1 for.
Sorry, all right. What I was saying is we have 2 separate sums to be accounted for here because we have the 1 4 5, which sums to 10, and the 1 5 5, which sums to 11. So basically these, and we have already established basically that these are all the possible cases where we can actually have the product of our scores go to at least 20. And note that the order of these numbers actually doesn't matter because, again, what we're doing is we're adding all of the scores together. And because of commutativity of addition, that result is going to be the same no matter how we arrange the numbers. So that means that we have already determined all of our cases, which gives us a grand total of how many cases?
It seems like we have 6 cases.
Yes.
6. And let's see if that answer is right. Ooh, seems like it is.
All right.
All right. Ooh, we have an algebra one. The expression x squared plus px plus q is the square of the expression x plus a. Given that p, q, and a are positive integers, what is the sum of the values of p plus q corresponding to the values of a that are less than or equal to 20? All right. This seems pretty cool. So first, what are we given? The expression x squared plus px plus q is equal to x plus a squared. Now, this seems a bit complex at first, but let's try and do a trick where we expand x plus a out, and by that we multiply it by itself. So, how do we multiply two binomials or two expressions with two terms together? Well, we use something called the FOIL method. So Marth, would you like to go along with that?
Yeah, sure. So the FOIL method stands for first, outside, inside, and last. And basically what this means in the context of multiplying binomials is you're going to multiply every term in this parentheses by every term in this set of parentheses. So first you multiply the first terms, x and x, which gives you x squared. Then you multiply the outside terms, x and a, and that gives you your second term is equal to ax. Then you multiply the inside terms, a and x, to give you another ax. And then you multiply the last terms, a and a, to give you a squared. So this is the result of actually multiplying these two values, and then when you put them all together and simplify, you get that this is equal to x squared plus 2ax plus a squared.
All right. 2ax squared plus 2ax plus a squared. That actually seems like a more doable result. And we're given that this is equivalent to the expression x squared plus px plus q. So I think we can represent p and q in terms of a. So in this case, p is just equal to 2a and q is equal to a squared. And we're asked to find the sum of the values of p and q corresponding to values of a that are less than or equal to 20. So in this case, what we should do is, the phrasing of this problem suggests that we plug in any value of a that's less than or equal to 20, from 1 all the way to 20. Is there a fast way to do that though?
Right, let's brainstorm for a second. Let's see what the possible values of p and q can end up being. So first let's try when a is equal to 1. Then we get that p is equal to 2 and q is equal to 1. When a is equal to 2, we get p is 4 and q is 4. And when a is equal to 3, we get that p is 6 and q is equal to 9. So what I'm noticing is that both of these seem to form their own little sets of patterns. The p's all seem to be, the p's are all 2 times a, so they form an increasing arithmetic sequence of the form a sub n is equal to, sorry, let's avoid that notation. They're forming an increasing arithmetic sequence, 2, 4, 6, all the way up to 40. Do we have a fast way to actually sum all of the values in this series?
I think we do, because I remember a trick where the sum of the numbers of 1 plus 2 plus 3 all the way to a number n is equal to n times n plus 1 all over 2. Now, these are for consecutive numbers, and these, while similar, don't seem like it. However, they're quite close, because what if you multiply all of these terms by 2? Well, you get the series 2 plus 4 plus 6 all the way to 2n. And if you multiply this by 2, you cancel out the denominator, meaning you get this is equal to n times n plus 1. So what do we have here? We have the numbers 2, 4, 6 all the way to 40. 40 is equal to 2n, so n is equal to 20. Now, if we plug in 20 to this equation, we just get 20 times 21, which is equal to 420. So that's for first. So we found the sum of all the p's. But is there a quick way to try and find the sum of the q's?
Let's see. So the q's seem to form an increasing sequence of squares going 1, 4, 9, all the way to 400. Now, I remember that there was also a very clean formula for the sum of consecutive squares. And if I remember correctly, it was 1 squared plus 2 squared plus all the way up to n squared. This sum is equal to n times n plus 1 times 2n plus 1 all over 6. Correct me if I'm wrong.
That seems
Okay.
like I've seen that before. Yeah, it seems like that would work. So let's figure out what our n squared is. Well, our last term is equal to 400. But what's 400? Well, that's the square root of 400 is simply equal to 20. So just like the last time, we have to substitute n is equal to 20. So if we substitute n equals 20 to this, we get 20 times 21 times 41, all divided by 6, which seems a bit hard, but let's try and common factors. 6 is just 2 times 3, so we'll divide this by 2 to get a 10, and divide this by 3 to get a 7, and that'll remove this. So we get 10 times 7 times 41, which is equal to 70 times 41, or 2870.
All right. So we have the sum of our squares, and we have the sum of our consecutive numbers. But remind me again, how does this relate back to our original problem?
Well, our original problem, we were asked to find the total sum of p plus q corresponding to values of a that are less than or equal to 20. In this case, we found the sum of all such p's, which is 287, of sum of all such p's, which is just 420, or 420, and all such q's, which is equal to 2,870. So we found sum of p's, we found a sum of q's. I think we just add these two up. What do you say?
I agree. So just when we add these two values up, we get that our final answer should be equal to 2870 plus 420, which is equal to 3,290.
Hmm.
Do you agree?
That was a pretty, yeah, and I think that should be right. Let's see.
Let's double check. And it
Yep.
looks like we got it. On to the next question.
All right. That was actually a pretty cool algebra problem. I haven't seen one like that before. All right. Non-negative
Non-negative
integers.
integers. Sorry, Arth, go ahead.
All right. Non-negative integers a, b, c, and d sum to 6. What is the expected value of a, b, c, d? Ooh. Express your answer as a common fraction. So first, what's expected value, Saharsh?
Sorry. The expected value is basically how do I explain this? The expected value is the total sum of how do I explain this simply? Do you want to try explaining it? I have a feeling my explanation might be a little bit too convoluted.
Well, in general, the expected value, let's say you have a lot of different cases, but each return a different number. For instance, there's a 10% chance you get 100 on your test, but if 90% chance you get a 80. Well, the expected value is basically what is your predicted value. In this case, let's say you have a 10%, or, okay, this is an example, 10% or 0.1 chance that you get a 100. So you multiply 0.1 by 100. But there's a much more likely 90% chance, or 0.9, that you get an 80. So you multiply 0.9 by 80. 0.1 times 100 is equal to 10, and 0.9 times 80 is equal to 72. If you add up 10 and 72 together, you get the value of 82. 82 is your expected value for the test. You're expected to get that. This is just an example, by the way.
Yeah.
So,
All right. So now let's think about how we would actually solve this problem. First, we should probably figure out some expectations for what A, B, C, and D are kind of going to look like.
I agree with that. So we're given that non-negative integers a, b, c, and d, that is a plus b plus c plus d, all sum to 6. Now note that they're non-negative. That crucially means that they're non-negative. They're not negative 1, negative 2, or anything, but they're all positive numbers. So 1, 2, 3, 4 plus 0. 0 is going to be an important part of this problem. So let's take a look at this. Let's take a look at a case. If you put 0 for A, put 2 for B, 1 for C, and 3 for D, you get it equal to 6. Now, what's the expected value of A, B, C, D? Well, right now we're given A, B, C, D in this case is 0 times 2 times 1 times 3, or just 0. And the expected value of A, B, C, and the expected value of this, what's the probability that for any any numbers A, B, C, D, we get this combination. We get this combination, or actually, let's make this a bit better. If it's in this case, we don't have to assign a specific number to each of A, B, C, D. Rather, if we have it 0, 2, 1, and 3, those can be assigned to any different number. So instead of A being 0, C could be 0, A could be 2, B could be 1, and D could be 3. It could be something like that. So how many different ways can we distribute these four numbers among A, B, C, D? Samarth, what do you think we should do?
In this case, because all of the numbers are different, we can consider the assignment of each number as basically a permutation on the number of ways to arrange the numbers 0, 1, 2, and 3. And in that case, we would have 4 factorial ways to get this specific combination, which is equal to 24.
4 factorial is equal to 24. Pretty good.
And now
But
we can do a similar process like this with a lot of other sequences too. But then the challenge becomes, how are we actually going to find the number of how are we actually going to find our sequences that end up summing to the value that we want? Is there any
well,
trick maybe we could use here?
there is one trick I know. It's a really cool trick I learned. It's a really cool trick I learned back in middle school, known as stars and bars. Let's say in this case, right, we're given that A plus B plus C plus D is equal sum to 6. It has to sum to 6. It's guaranteed. What if we represent it as 6 stars? Well, if you represent this as 6 stars, then we can split up and so we have 6 stars. A, B, C, and D have to be pooled together among these 6. Now, this is where the bars come in. Let's say A is equal to 1. So this is the A section. B is equal to 2. This is the B section. C is equal to 2. That's the C section. And then D has the remaining star. I think this approach works fine. But also, you guys might be asking, what if all the bars are on one side? 1, 2, 3, 4. But then all the 6 stars come. That way, none of the letters except for D get the stars. Well, that's fine, because Samarth, you know what this problem says?
It says that our integers A, B, C, and D are non-negative integers, which means that they can have no stars in front of them or in between them, which would correlate to a value of 0.
Exactly. So, correlations correspond to a value 0. That's exactly right. So I think with stars and bars, we can get the total amount of cases which we have to work with. So what's the formula for stars and bars, Samarth?
So one way I really like to think about this is I know how I could have strictly positive integers A, B, C, and D sum to a value. If I had 6 stars and I needed 4 strictly positive integers to sum, then I would just imagine drawing bars in between each of these lines. But we're allowed to have non-negative integers. So one way I like to think about it is I imagine already assigning to A, B, C, and D 1 star. And then I think about how many ways I could give them values to sum to that plus the number of variables there actually are. So in this case, because we have 4 non-negative numbers summing to 6, the total number of ways to divide them up would be equal to 6 plus 4 minus 1, choose 4 minus 1, or 9 choose 3.
9 choose 3. I think this will be pretty good because, guys, if you recall, the choose function n choose k is simply equal to n factorial over n minus k factorial times k factorial times k factorial. In this case, we're given that 9 choose 3 is equal to 9 factorial divided by 9 minus 3, 6 factorial times 3 factorial. Now 9 factorial is just 9 times 8 times 7 all through 1. But 6 factorial, you can divide it. So all the numbers 1 through 6 are divided. You get 7 times 8 times 9 divided by 3 factorial, or 6. Oh, and 9 choose 3 basically just represents the amount of permutations or amount of ways you can order an object. Isn't that correct, Samarth?
Yeah, just to be a little bit more specific, right? So when we think of a permutation, we think of a permutation as a way of taking objects and like ordering them. So in the context of our stars and bars example, what this would mean is, like, let's say we had 4 bars, or in this case we had 3 bars. We could name this one like bar 1, bar 2, bar 1, bar 2, and then bar 3. And then let's say we wanted to pick slots in between each of these stars to actually put ours into. Then the number of ways to actually pick, oops, the number of ways to actually pick slots for each of these bars would be equal to 6 times 5 times 4. Because we would pick one slot for bar 1, one slot for bar 2, one slot for bar 3. Sorry, that should be 5 times 4 times 3. But when we say choose, we are actually accounting for the fact that our bars in this case don't actually have identities. Instead, we're simply trying to pick the number of ways we could select 3 different slots to put bars into. So, in this case, 6 factorial over, in this case, 5 factorial over 2 factorial represents the number of ways to actually select three different slots, one at a time. And then we again divide by 3 factorial because for every single way we could select 3 separate slots, we will have done that 3 factorial different ways. Because we can place, when we choose those 3 slots, we can place the bars 1, 2, and 3 in them in any order. And there's 6 different ways to do that. So that's what the purpose of so basically the choose function, or the binomial coefficient here, represents the number of ways to pick, it represents the number of ways to pick, the bottom number of objects from, this many options, where you don't care about the order in which you pick them.
That seems like a great explanation, and yeah, that seems like it worked. Does that work? Type in the chat if that makes sense to y'all.
All right. While we're letting that fester a little bit, now let's think about actually getting to the values of A, B, C, D that are possible. So we know one thing we can figure out pretty quickly is that we need all of our values A, B, C, and D to be positive if we want this if we want this multiplication to have any value. If any of our numbers are 0, then the whole thing will evaluate to 0. And without loss of generality, we know that the only combinations of numbers that actually get us to our final answer are 1113 and 1122 in some order. Any other, if we were to try to increase any of these numbers, then we would end up forcing ourselves to have a 0 as another value, which would cause the multiplication of all 4 to end up as 0.
Right. In case you'd missed something, we're not counting the cases with 0 as they add nothing to the equation. We can just disregard them. So in this case, we're given numbers 1113 and 1122. I think, and we just have to find the amount of ways we can distribute each of these. I found that there's actually a pretty cool trick which we can do, where if you're given, let's say, because here we're repeating a lot of numbers. Versus this case, we have 3 1s and 1 3, and second case 2 1s and 2 2s. You can just do, how many different ways are there? Numbers are there? There's just 4 factorial numbers, but there's 3 1s, there's 3 1s and 1 3. Since there's 3 of the same character, we can divide 4 factorial by 3 factorial, and there's 1 3, we can divide it by 1 factorial. So that 4 factorial divided by 3 factorial is just equal to 4. So there's 4 different ways where this can be, there's 4 different ways where this can be organized. Let's apply this trick to 1122. Let me move to a different thing. Right. So 1122, there's 4 characters, and in this case, there's 2 2's, so 2 factorial, divide that by 2 factorial, and then 2 1's, so 2 factorial. This is going off some Martha explanation from before about factorials and choosing stuff. So 4 factorial divided by 2 times 2, so 4, is just equal to 6. So what does that mean? So we've established that there are 84 possible ways to choose something. So we just 84. How many ways are there to choose 1113? Well, we've established that there are 4 ways. And what about 1122? Well, that's equal to 6 divided by 6 ways over 84, so 6 over 84.
Not so fast. We're missing one really quick step. What we're trying to figure out isn't the expected number of permutations that gets us to a non-zero multiple. We're trying to figure out the expected value of A, B, C, D. So, in case you guys don't remember, the way expected value works is you actually take all of your possibilities and you take the number of possibilities or in a more general sense, you take the probability that the possibility occurs, and then you multiply it by the value that's actually assigned to the possibility. So in this case, we found that there are 4 ways to get 1113 and 6 ways to get 1122. And now keep in mind that each of these like combinations of numbers is actually assigned a value, which is the product of the 4 numbers. So in this case, we have 6 ways to get 1122, and 1122 is associated with 4 because 4 is the product. Similarly, 1113 is associated with 3, which is the product of those 4, and there are 4 ways to get that. So we would multiply 4, the number of possibilities, by 3, which is the actual value of the possibilities that we care about. So when we combine these two, we get the total possible value of all products across all possible values of A, B, C, D. Right?
Right, and that makes sense. So, if we're proceeding with this operation, 4 times 3 is equal to 12, and then 6 times 4 is equal to 24. 12 plus 24 is equal to 36, so our fraction is 36 over 84, but we're not done yet. Remember, as some of you guys pointed out in the chat, we always have to simplify. So, what is a common factor between 36 and 84? Well, I think that it's going to be 12, because 36 is simply equal to 3 times 12, and 84 is just equal to 12 times 7. So if we cancel out the 12s, we get 3 over 7.
Which I saw some people mentioning earlier on in the chat. So good job, guys. You solved that question incredibly quickly.
Yeah, keep it up, guys.
And now,
All right,
double
let's
check.
see.
It looks like we are correct.
Perfect. All right, let's try and go through this quickly. What is the sum of the lengths of the altitudes of a triangle with sides of length 13, 14, and 15? Express your answer as a common fraction. So Samar, this seems like it would be really well. Let's see. Let's remember our general triangle area formula. The area of triangle ABC is just equal to 1/2 times the base times the height. But we're not given anything like that here. We're just given the side lengths. So how do you think we could find the area if we're just given the side lengths?
That's a good point. I seem to remember that there was actually a general formula for the area of a triangle given all 3 of its side lengths. Or do you want to remind me what it is?
Yeah, I think it's called the Hadron formula. No, Heron's formula. There we are. Heron's formula, as I remember, is going to be equal to, Heron's formula states that the area of a triangle with side lengths A, B, C is equivalent to, and guys, just a quick heads up, this is going to be a long formula, is equal to the square root of the semi-perimeter, or the sum of all the perimeter of all the sides divided by 2 is equal to S. The area triangle ABC is equal to semi-perimeter times semi-perimeter minus side A, semi-perimeter minus side B, and semi-perimeter minus side C. So area is equal to square root of S times S minus A times S minus B, and S times S minus C. I see we got a cameo back in the background. So Samarth.
Sorry, guys. That was my roommate, Thomas. Thomas is actually an ex-Live alumni and absolutely amazing guy. I actually got to meet him, so. But anyways, back to the problem.
All right. So first, let's try and solve the semi-perimeter, because that's really crucial. We're given side lengths of 13, 14, and 15. Well, 13 plus 14 plus 15 is just going to be equal to 42. Divide that by 2, we get that equal to 21. Now, let's plug 21 back into this equation. We're given that 21 times 21 minus 13, which is equal to 8, times 21 minus 14, which is equal to 7. 21 minus 15 is equal to 6. We're given the square root of all of that is equal to our area. How do we quickly find this? Well,
I noticed that I was just going to say, I'm noticing that a lot of our prime factors are actually pairing up. So if we look at 3, we notice that 3 shows up once in 21 and once in 6. So we have, at the very least, a 3 squared in here. Now if we look at our 2's, we see that 8 is equal to 2 to the 3rd, and we get another 2 because of our 6. So we know that inside our square root, we also have a 2 to the fourth. And then additionally, our last prime factor seems to be 7. And we see that 7 shows up once here and once here. So we have 7 squared. And then
Nice.
this seems like it would be really easy to take the square root of. Arth, do you want to finish it up?
Yeah, sure. So we're given that 3 squared times 2 to the 4 times 7 squared. What's the square root of that? Well, square root is just multiplying all these exponents by 1/2. So 2 times 1/2 is just 1. So we're just given that as 3. Times 2 to the 4th. 4 times 1/2 is just 2. So 2 squared. Times 7. 2 times 1/2 is just 1. So so we're given 3 times 2 squared, which is just 4 times 7, which is going to be equal to 84. Now, that's the area. That's the area of our triangle, but we're given, but we're not. That's not. But we're not done yet. We're given that the area of this triangle is equal to 84. We have to find its altitudes. Luckily, we have we have a formula from before. The area of a triangle is also equal to 1/2 times the base times the height. In this case, we're given that the total area is 84, and we're actually given all three of the side lengths. So we can just plug in, and the altitude is just the height of a triangle, in case you're confused. So we just plug in 13, 14, and 15 separately for the base, and then we solve for the height. Do you think that'll work? Do you think that'll work, Samarth?
I do have a feeling that it'll work. I also don't think I'm quite willing to go through the effort of doing all of that multiplication out right now. But
So neither am I.
but I hope that you guys will double check this method, maybe take some time to plug it into your calculator yourselves, and figure out what the answer is for yourself. But just in case, do you want to reveal the answer for them to reference later?
Sure. And it seems that the answer is
2,000.
2,348 divided by 65. Oh, wow.
Cool. Cool. That's good. Actually, I was just looking at this thing. I just popped in at the end just to say hello. But this particular question, the 13, 14, 15 triangle, the more important thing is it turns out that you can make that out of 5, 12, 13 triangle and another thing which is similar to 3, 4, 5. Did you know that? Like, because if you work this out, you'll find that one of the altitudes is 12. So if you think about it, there's a 12 and there's a 13. Uh, I actually can't draw because I don't have the technology that you guys have. But if you draw like an altitude of 12 and then one side which is a 15, one side which is a 13. And if you think about it, so I got 12, 13, I got 13, 14, and 15. 14 is not a good hypotenuse for like a Pythagorean triple. Yeah, but the 3, 4, 5 you can. So then you can go slam two of them together. So that's actually where you get the 13, 14, 15 triangle from.
That's
Yeah.
actually really interesting, Professor
It's
Loh.
just like it's kind of cool. Like there's no reason why you would know this unless you did a bunch of these math contest problems. But if you did, then you're like, ah, the 13, 14, 15 is the sneaky triangle. So yeah, so that's there. But am I correct? You guys were basically at the time and you're about to stop.
Yes.
Is that right? Because I was
Yeah.
just gonna come in and say, my gosh, this halftime show is better than Bad Bunny. That's all I can say. If you guys are here, actually, I have no idea what I have. No, I didn't even look at the other halftime show, so I have no idea if the other one was good or not. But all I'm gonna say is that if you came to this live solve, somehow I think that means that you weren't watching the Super Bowl, or maybe you were at the same time. But who knows? Maybe you like this thing better. That's Bad Bunny. I don't know. I don't pay attention. I just know that there happens to be something called a Super Bowl right now, something like a halftime show, and you guys just got the Math League live solve halftime show. So thank you, Arit. Thank you, Samarth. Thank you to everyone else who joined. Have a great rest of the Super Bowl. Bye bye.
Thank you. Thanks, guys, for coming. Have a great rest of your weekend, and we hope to see you again soon.
Make sure you catch the rest of the Super Bowl, whatever's going on. All right.
Yep.
Bye bye.